Hi everyone. I hope you're all doing good. Sorry about the delay. Welcome to the grade 11 paper 2 live session that we're doing. So today we're going to be doing chemistry. To those of you that have been with us on Tuesday, welcome back. And to any newcomers, we will be working through some of the content you've worked through for chemistry this year, a little bit of revision on like what you've learned, and then also past paper questions and how to attempt them. Thank you. So also thank you to those who joined on TikTok. You're welcome to engage in the chat, and anything that you comment will be transferred over here to us in the chat. So I will be able to engage with anything that you say. Also, to those of you that have joined, please do engage as much as possible by talking and answering in the chat, asking any questions along the way. I'll try and answer all the questions you guys have. So in terms of what we are doing today, we are going to be working a little bit through our chemical bonding. So just all the different bonds that we have, all the different like factors that affect our chemical bonding. We're also going to be looking at Lewis diagrams very briefly. We will be doing some intermolecular forces, where we're also looking at the relationship between different forces and how that affects our melting points and our boiling points. And then just a little bit of stoichiometry, which would have been from last year. To my understanding, only chemical bonding and intermolecular forces have been done at a grade 11 level, where stoichiometry is kind of just going to be a little bit of revision from grade 10. So yeah, okay, let's jump right in. So we're starting off with our chemical bonding, just a little bit of understanding what our chemical bonding is, right? So we have a net electrostatic force between two atoms, right? And how that force is exerted on each other to kind of force these atoms to engage and stay connected to one another, right? The whole idea of chemical bonding is that we have unpaired electrons of different atoms will either transfer or share electrons. So it's all about that interactions with our atoms and specifically the electrons, because they're more, they have a lot more movement compared to the other subatomic particles. So the whole idea of chemical bonding has to do with electrons, whether we're transferring it, whether we're sharing it, or whether we have delocalized electrons. So before I move on to Lewis diagrams, I just want to ask you guys to tell me what the different bonds we have. So I'm talking about intramolecular bonds, the ones between atoms. So I believe we have 3 based on whether we're working with metals, whether we're working with non-metals. So can you do me a favor, and in the chat, can you just list the 3 different bonds, and preferably also what type of atoms they bond together? Cool. Thank you. Someone from TikTok told us that we have ionic bonds, covalent bonds, and metallic. Yes, you were right. Those are the 3 that I'm referring to. If the same person could also maybe just elaborate on which types of atoms are bonding in each. So like for metallic bonds, are we bonding non-metals with metals? Are we bonding metals with metals, non-metals with non-metals? Can you maybe just elaborate? This is also open to everyone else. So if you know which types of atoms are bonded to each other in the different types of bonds, please do tell me. Just, I want to gauge how much you guys know and how much you understand. Okay, so our ionic bonds, person from TikTok said an ionic bond is non-metals and metals, covalent are between two non-metals, and then our metallic are metals. Perfect, thank you so much. So in terms of knowing the structure of it, right? You kind of, by structure, I mean just knowing how the bonds form, right? So I think one of the easiest ones that we have is our metallic bonds, right? So let me draw it out for you guys. Sorry, just have to get my pen out quickly. So in terms of how our metallic bonds look, we have this idea of the positive kernels as well as a sea of delocalized electrons. So in terms of how that looks, let me just draw this out for you in this little space here. So this is our metallic bonds. We kind of have these positive kernels, and by positive kernels, we're kind of just talking about the nucleus of atoms, right? Which are kind of close to each other, touching, and then we have this sea of delocalized electrons floating around them, right? And what that means is that delocalized means that it's not stuck in a specific orbit, right? So these electrons can flow consistently throughout this entire medium. It's not specific to a nucleus or a specific atom. They delocalize, meaning that they can move. And this is one of the reasons why metals are conductors, right? So conductors, just to remind you, in electricity, are substances or mediums that allow electrical flow through. And our electricity is that movement of charge, right? And our charge is our electrons. So the reasons why metals are conductors is because we have these free-flowing electrons that can actually allow charge through it or allow to move, right? So that's what electricity is. Okay, so that's just our metallic bonds, right? Then we have this idea of an ionic bond, right? So ionic bonds kind of give you a hint in the name where we're going to be working with ions, right? So we kind of form ions because it's the whole idea of transferring electrons. So if we have an atom that has a set amount of electrons and we transfer those electrons to another, then this atom will become more positively charged, whereas this one, because it's gaining electrons, it will become more negatively charged. And then obviously charged atoms are called ions. So the whole idea of ionic bonds is that we're transferring these electrons, changing the charge of each atom and forming ions, right? And like the person in the comments said, that our ionic bonds are between metals and non-metals, right? And the last thing we have is covalent bonds. And our covalent bonds are between two non-metals. And that is the idea of shared paired electrons, right? So what that means is that we don't have this transfer of electrons. We don't have this movement of electrons. There'll be two atoms that have electrons between them, and both of these atoms will share this in order to fill that octet rule. Because remember, octet rule is the idea that each atom is striving to have a full outer orbital, right? And the outer orbital needs a maximum of 6 electrons. So sometimes to fulfill that rule, we have to share electrons between two atoms where both of them have access to both electrons. Okay, so that's just a brief, very quick reminder of your 3 different chemical bonds. And remember these bonds, these let me change the color to white, or actually black, sorry. So our chemical bonds, these 3 chemical bonds are referred to as our intramolecular bonds, right? Which you need to remember are different to your intermolecular bonds. So we'll get to that later, but just remember that these chemical bonds are typically referred to as intra, right? In this idea of the RA, the tra, that typically in biology and chemistry means within, right? So within something. So here, if we have a molecule, intramolecular bonds are the bonds within the molecule, as opposed to the bonds around it. Okay. If you have any questions, drop them down in the chat. I'll try read them and carry on. But moving on to this idea of Lewis diagrams. Right. So you did touch on this last year in grade 10. It's not much more complex. There's nothing really much different compared to what you did last time. The whole idea of your Lewis diagrams is just showing where electrons sit, where in specific molecules and specific compounds, right? So the whole idea of Lewis diagrams is that we are looking at our valence electrons, right? So you are able to determine your valence electrons based on looking at your periodic table, right? So I actually didn't add a periodic table here, or maybe there's one further down. So here's one where you have the different numbers above your different groups and different periods that represent different things, right? So this is +1, +2, +3, +4, plus or -4. And that's -3, -2, -1, and 0, right? So these numbers give you indication of what your valence electrons are. And then from there, you're able to draw your Lewis diagram and try and figure out how different molecules and different compounds actually share those valence electrons and how they would be structured, and then also the molecular shape of it, right? So just to run through some examples and how to really go about drawing out your Lewis diagrams, we have, let's take an easy example like H2O, right? So we know hydrogen has a valency of 1. So it has 1 electron, right? We have 2 hydrogens, so they're going to be like this, right? Oxygen, we know, has a valency of 6, right? So how I like to do it is drawing my electrons in clockwise, just for them to be orientated a very specific way, right? So remember the whole idea of chemical bonding and chemical bonding, sorry, another word slipped my mind. We are trying to strive for that octet rule, right? Where we're trying to have all 8 electrons in the outer orbital. And remember, I said with like covalent bonding and all the stuff, we can have shared pairs of electrons, right? So here for H2O, what's going to happen is our hydrogen only needs 2, right? Because hydrogen is such a small molecule, such a small atom, that it only needs 2 electrons, right? Whereas our oxygen wants the full 8, right? So we are going to share these sets of electrons with each other so that hydrogen receives 2 and oxygen gets 8, right? So in terms of how the compound would look, you'd have something that looks like this, right? Where you can see there's the shared pair of electrons between our hydrogens and between our oxygen, right? Remember, just for ease of your marker, that different electrons from different atoms must be represented differently, where they prefer the dots and the X's, just so they can distinguish which electrons correspond to which atom, you know? Then just another example is a more challenging one, if you will, because so those were single bonds. Sorry, I should have actually drawn that out. So another way it can be written is if you have a shared pair of electrons or 2 electrons between an atom, it's a single bond, right? And we still have our lone pairs over there, right? But now where they test you with a few harder examples is where you have double bonds or where you have triple bonds, right? So the example of this acid HCN, right? So let's break it down. We firstly need to take a look at each of the components in each of them and what their valence electrons are. So we know hydrogen is going to have a valency of 1. I'll even scroll down to the periodic table for you. Carbon is sitting over here. It has plus minus 4, meaning that it has 4 electrons, 4 valence electrons. So my carbon is going to have 1, 2, 3, 4. And then my nitrogen, you can see it's over there, right? And it will have 5 valence electrons, okay? So we go back up, and our nitrogen is going to have 1, 2, 3, 4, 5, okay? So we know that the way our atoms are going to react here is the hydrogen is going to bond with the carbon, right? So we know that for certain. This hydrogen is going to share this electron with the carbon there. And now we can see that this nitrogen is missing electrons there, there, and there, right? So it needs 3 more electrons to meet that octet rule to get a full 8 electrons in its outer orbital, right? And now we can see that the carbon, this is already gone, but it has 1, 2, 3 electrons to still give, to still react with the nitrogen. So what happens is we then will form actually a triple bond here, where we have all our electrons from our carbons lined up, and then the unpaired electrons from the nitrogen will also line up here, and then we still have our lone pair over there, right? And then that would be represented as a single bond between the hydrogen and the carbon, and a triple bond between the carbon and the nitrogen, right? So it's not always very simple. It's not always that you just have a single bond. Very often you just have to make sure you obeying that octet rule. And then sometimes you can get double bonds. Sometimes you can get triple bonds. It depends on the example that you're working with, right? So then I think this is where it starts getting a little bit more complex for grade 11s, is we work with the VSEPR theory, right? So this is where we're actually taking into account the molecular shape of the different compounds and the different molecules that we're working with. So it is a bit daunting. It is a bit scary. You think, like, how the hell am I going to figure this out? But this table over here actually breaks it down for you quite nicely, in a sense that you look at the number of bonding pairs that you have, and then also take a look at your lone pairs, because the lone pairs is what's responsible for actually shifting the angles, right? Because if you have, let's take, for example, this HCN over here, this, or these lone pairs over here in the water, right? These electrons are gonna, to some extent, repel the hydrogen and the hydrogen's electron orbit, right? So that's the reason why you kind of get that bent shape for certain things, because the unpaired, sorry, the lone pairs, sorry, that word escaped me. The lone pairs will actually change the shape of your molecule because they will exert forces on the other atoms that are present, right? So over here, you can see that with your linear, you typically have 1 or 2 bonding pairs, right? Where the bonding pair is the electrons that are actually between the two things. So this like single bond over here, or the double bond or the triple bond over here, right? So those are considered your bonding pairs, right? So if you just have 1 or 2 and you have no lone pairs, then it's typically going to be linear. It's just going to evenly distribute out something like this over here. And here we have a different annotation for our molecular shapes, right? You could also, so here's just 2 atoms binding, so 1 bonding pair, but then here still we have 3 atoms binding, so there's 2 bonding pairs, but still there are no lone pairs, so then we don't have that bent shape or anything, right? Whereas if we move on to our bent, right, we're still working with two bonding pairs, but now we actually have lone pairs, right? So like I said, those lone pairs are gonna kind of shape your molecule, because now there's going to be force of repulsion, right? So if we take water, for example, water could very easily look like this. It could be linear, right? If we didn't have those lone pairs. But now that we have those lone pairs present, what's going to happen is this is almost too close, right? So there's going to be a force of repulsion, because if you think back to electrostatics, where you have like forces, they're going to repel each other, right? So that force is these lone pairs are going to force these bonds further away, which results in a more bent shape of the molecule, right? So water is an example of a bent or an angular type of molecule, okay? Because we have two bonding pairs, but we also have two lone pairs present, resulting in our bent or angular, right? Luckily for us, in this table, they did give us general formulas, right? So if we were to take, for example, let me just think of one, CCl4, right? If we were to take, so naturally you wouldn't really know you can figure it out. Let's kind of work with the Lewis diagram. So we know our carbon has 4 valence electrons, whereas our chlorine, let's go down to our periodic table, it has 7, right? So our chlorine's gonna look okay, so our chlorine is going to look something like this. So all of it's obeying the octet rule, because for our carbon, it has 8, and then our chlorine all has 8, right? So in terms of how this will look, it would be kind of hard to picture it, right? And you wouldn't really know, okay, is there any bends or whatever? But luckily, if we come to this table here, we can see, okay, there are 4 bonding pairs, right? Over there. And then we can see we have I guess we do have a certain number of lone pairs here, but they're all balanced. There's not an unequal distribution of them. They're all balanced throughout the entire molecule, right? So it's fine. That's why this wouldn't really have any bend. And then we can see here that it would be tetrahedral in its shape, right? But let's say for some reason you really still couldn't understand that, or like it was a complex thing. Here actually gives you general formulas for each of the shapes. So the A can be anything, the X can be anything. So in this case, I chose carbon for my A and chlorine for my X. So I didn't really need to even draw this out to figure out if it had a certain number of bonding pairs and certain amount of lone pairs. I could have just used this general formula to figure out which shape. But obviously that just depends on the questions they ask you. Typically, they ask you to draw the Lewis diagram and then work towards figuring out the shape. But if you want a quick and easy, like cheat sheet, if you will, this table is quite nice because it just gives you the general formulas that you can use to figure out the shape of the different molecules that you're working with. So the VSEPR theory, I know a lot of students struggle with it. They find it a bit daunting, and I will admit it is a bit daunting. But honestly, the more you practice, the more familiar you get with understanding how many lone pairs there are and bonding pairs and whatever, also the general formula, it really isn't that scary. So the more practice you do, the more you'll get comfortable with it and the more it will make sense to you. Okay. Again, guys, if you have any questions, put them in the chat. I'll try and address them as soon as I see them. Okay. But now let's move on to electronegativity. So I'm just going to erase what I've drawn here on our periodic table. So electronegativity is this idea of the measuring an atom's ability to attract a shared pair of electrons. So electronegativity is only really appropriate or like necessary in covalent bonds, right? Because covalent bonds is where we're sharing electrons, right? So the whole idea of electronegativity is just also figuring out if something is polar or non-polar, right? So polar means that you have an uneven distribution of charge. So if we were to take, like, let's say this is our electron cloud of an atom or of a compound, right? There could be some areas that are more densely negative and some that are more densely positive, right? So polar means polar opposites, right? Opposite ends, where there's an uneven distribution. So we end up having a more positively charged side and a more negatively charged side, right? So what your electronegativity does, it affects polarity of a molecule because it depends on where our electrons are actually sitting, right? So if the typically with electronegativity, we figure out whether something is polar and non-polar based on the difference of electronegativities, right? So this periodic table here is just showing us how electronegativity changes and the trends of it throughout our periodic table, right? So as you can see, as we move across our periodic table, you can see that our electronegativity is getting greater, right? Meaning that oxygen will have a higher tendency to attract a shared pair of electrons compared to our hydrogen. So again, if we take water as an example, see water as an example, these are bonding pairs. These are shared pairs of electrons, right? But because oxygen has a higher electronegativity, that means that the electrons will actually stick closer in proximity, literally in distance. It will stick closer to our oxygen compared to our hydrogens, right? So I did leave a bit of a gap there just to emphasize it. But I'm just showing you that because oxygen has a greater electronegativity compared to our hydrogen, the shared pair of electrons will have a tendency to stay attracted to our oxygen compared to our hydrogen, right? And the reason why this will affect our polarity is because now, if we were to draw our electron cloud around this, our hydrogens don't really have much of an electron cloud because our electrons are so far away from it, right? Whereas our oxygen now has this massive electron cloud because look how many electrons are around it, right? So this will be very negative on this end, whereas on this end, it will be more positive. So we have that uneven distribution of charge, where now we have a more negative region of the molecule and a more positive, resulting in this polarity, okay? So your electronegativity, how you gauge whether something is polar or non-polar, you typically look at your difference in electronegativities. So that literally means looking at the electronegativity of one atom and comparing it to another, right? So here we can see they've given us values on this periodic table. So we'll stick with water and oxygen, where this is 3.44 and this is 2.22, right? So calculating the difference, I'm literally going to take 3.44 and minus 2.22, right? Which will give us a value of 1.2, right? So now where this becomes important is you are taught different scales, right? So you're kind of taught on a number line or on a scaling thing where something is polar, non-polar, or even ionic, right? So typically any value less than 1, so anything down here is we will have covalent bonds and they will be weak polar, right? So what that means is that it will be a polar molecule, but it's not going to be very distinct. So here I kind of over-exaggerated this water, but you can see that it's very distinct, that we have a negative side and we have a positive side, right? Whereas with weak polar, you'll kind of see an electron cloud where it's just a little bit more negative over here and more positive over here, where it's just about barely polar, okay? Then anything between 1 and 2, anything between this range, you typically have polar covalent. Right? So what that means is we're still working with covalent bonds, but they just very polar. So this would be an example of being quite drastic in terms of the polarity. And we can see that that's true because the difference in electronegativity is, but it's 1.2, which sits between 1 and 2, right? Obviously on the lesser region, but still sitting within that range. And then anything above 2.0 would be our ionic bonds. Okay, so typically in questions and stuff, they ask you like, oh, would this molecule be polar? And the only way you can figure it out is by calculating the difference of electronegativities. And also knowing this range over here is quite important for being able to distinguish if something is polar or not. Also, just over here in terms of 0, if our electronegativity for some reason is 0, then that means that we're still working with a covalent bond, but it is just non-polar, right? So there is no difference in charge. It's overall the same charge throughout the entire compound, throughout the entire molecule. Okay. So there are still like bond energies and bond lengths, but I was hoping that that was like fairly simple enough, so I didn't really cover that. So I just covered these aspects of chemical bonding. So what we're going to do now is work through a question. Okay. So on Tuesday, I kind of was working through it myself and showing you the steps and then wanted you guys to kind of engage. Today, I'm going to try and have you guys do the bulk of the work. This one's fairly easy because you kind of just have to give definitions and match whichever of these following compounds is relevant and whatever. So I'm hoping really to get a lot of engagement from you guys because that is how you benefit. Because it doesn't help me sitting here doing everything. If you got, the more you guys engage, the more you understand the work and the better you'll do, right? So I've highlighted the specific questions I want us to work through because I don't want us to necessarily do all of them. So for 2.1, just to define the term molecule. Molecules and compounds are different. Molecule has a more specific definition. So if someone could please drop it down in the chat for me, what you understand the definition for molecule to be. Okay, so I'm going to give you the definition of a compound, right? Because I think a lot of people have this idea that a compound and a molecule are kind of the same thing. They're very similar, but a molecule has more specifications, right? So the definition of a compound is simply just two, it's essentially a mixture. So it's two different elements that are chemically bound together, right? So what I want to know is now, what is the difference between a compound and a molecule? Because in my head, they're relatively the same thing. So what's different from a molecule? Okay, we have Kano that says, a molecule is a group of two or more atoms held together by chemical bonds. Okay. So kind of you're going to have to be a little bit more specific with your answer there, right? Because then we have someone that said a group of two or more atoms that are covalently bonded and act as a function. There we go. Perfect. Word for word. So kind of you were right in the sense that we are having two or more atoms that are held together by chemical bonds, but you just had to be specific about which bonds, right? You had to specify that it's covalent bonds and that now that they're bound, they act as a function. So they act as its own entity, if you will. Okay. Um, so well done. Thank you to you two for contributing. Cool. So then they've given us these lists of compounds, right? And now they want us to almost match the descriptions to each of these, right? So a dative covalent bond. So I actually didn't touch on this. What is the difference between a dative covalent bond and a covalent bond? Like, why are we specifying dative? What does that mean? Okay, let's see what someone said. Bonding between two nonmetals. Okay, cool. So that is what a covalent bond is, right? We have that bonding between two nonmetals, and it's the idea of a shared pair of electrons, right? But now a dative covalent bond is something more specific. Okay. I'll give a second to someone that was typing an answer there. There we go. Cool. Thank you, Chiabetswe. A dative covalent bond is one atom providing both electrons, right? So it's still the idea that we're sharing electrons between two atoms, but now it's such that both that shared pair of electrons, actually both of those electrons come from one atom. So let me just quickly think of an example. Okay, I can't think of a specific example, but let's say we have um, compound X, right? That has typically with your noble gases, because they already have your full outer orbital, sometimes they will react with other things to help them fill their orbitals, right? So let's say compound X has a full 8 electrons in the outer orbital, and compound Y only has 6, right? So obviously they only need 2 more, okay? Compound X doesn't necessarily need anything from compound Y, but in order for them to bind, what can happen is that compound X provides the full shared pair of electrons. So compound Y just quickly binds onto compound X, and now this is the bonding pair, this is the shared pair of electrons, but both of them are coming from compound X. Okay, thank you for giving me an example here, Betwe. But I think we'll just stick with this basic analogy, right? So now, based on the options that we have here, which of these do you think would be a dative covalent bond? Number two. Okay, you said number two. Let's take a look. So number two is that hydronium. So it's that H3O plus, right? Okay, we have two people saying that. So let's take a look. Let's actually draw it out for ourselves. Let's do the Lewis diagram to figure out. Okay, so we have hydrogen, which we know only has one electron. We have three of them. And then we have an oxygen, which we know has, six electrons, right? So already we know that like, okay, water, we're going to have relatively the same thing where we have something like this. But now we have this additional hydrogen, right? What can happen is because it's positive, we know that we're going to have, it's going to lose an electron, right? Because it's an ion now. It's positive, so we've lost that electron, right? So what happens is now actually this hydrogen comes and binds over here with to get these two electrons, right? Because now this is a dative covalent bond because there's a shared pair of electrons between these two atoms, but the electrons are coming both from the oxygen, right? So that would be an example of our dative covalent bond. Okay, so nice. So this was our correct answer for 2.1.2, right? Then 2.1.3 asks us which out of all of these options would have ionic bonds. So to remind yourself, ionic bonds are between nonmetals and metals, right? So which of these do we have nonmetals and metals binding with one another?
Apologies, everyone. We're just having some technical difficulties. Please bear with us.
All right, sorry about that. I'm not sure why I disconnected there for a second. Sorry about that. Let me just start sharing my screen again. Okay. Let me know if there's any issues with the screen share, but hopefully everything's fine. Sorry, I don't know what happened there, if it was connection issues or what. So, carrying on with what we were doing. So, we were on 2.2, drawing the Lewis structure for the molecule. So I only wanted NH3, right? So I know it's going to be a little bit hard for you guys to really engage here, but I want you to try your best. So maybe what you can do is just tell me what the valency is for each of the atoms here. So what is the valency for nitrogen and what is the valency for hydrogen? So just kind of guide me on how you would attempt this in a paper. Yeah, I'm not sure if you guys have periodic tables with you currently, so I'm just going to come up here for you. So just tell me how many valence electrons does our nitrogen have and how many valence electrons does our hydrogen have? Okay, cool. So hydrogen has one valence electron, and then our nitrogen, 5 valence electrons. Perfect. Thank you. Okay, cool. So that's always where we start with our Lewis diagrams, right? We start off with just figuring out how many valence electrons we're actually working with. So like you said, hydrogen has one and nitrogen has 5, right? So what we need for our nitrogen, it needs 3 electrons to fill that octet rule. Lucky for us, we have 3 hydrogens that are bonding, and each hydrogen only has 1 electron. Okay, thank you to everyone in the chat that's contributing. So in terms of how this will look, we will obviously just move the hydrogens in places of each of these bonding pairs that we need, these electrons that we need. Okay, cool. So step 2 from Giabetswe, they ask us, or they tell us that step 2 is to choose the central atom. So, and you said our central atom is nitrogen. Perfect, cool. Because nitrogen has the most electrons and our hydrogens are going to bond to the nitrogen. So our nitrogen is our central atom. Nice. We have our hydrogens all around it like that. And then we obviously have to put in our respective electrons for the hydrogens, which would go something like that. Cool. And you draw single bonds. Yes. So once you've shown the electrons, you can take it a step further and show the single bonds between each of the atoms, and then also just keeping your lone pairs present as well. Right? Nice. Thank you. So now, no, we're not going to do HCN just because I did it as an example, but just remember that it doesn't always need to be single bonds. You can also have double or triple bonds, right? Then 2.3 asks us how many lone pairs of electrons are in one molecule of NH3. So it's kind of there for you, but I still want you to tell me in the chat, how do you identify a lone pair, and then also how many? Okay, so here it's where you say there's one. Cool. And the way we identify a lone pair is, remember, it's a pair of electrons that are not bound. So they're not the bonding pair. So in terms of what our lone pair would be, it would be this lone pair of electrons over here. And here Bettsway was right in saying that it's 1. Okay. Then BCl3, right? They ask us if it's polar or non-polar. So remember, that's the idea of if there's a more positively charged side and a more negatively charged side, right? They may ask us to explain our answer by referring to the molecular shape, okay, and polarity, right? So what I'm going to do is I'm going to do you a favor and come up here to this again. So let me just erase what we have over here. Change this to white. So they asked us about BCl3, right? So we can do the Lewis diagram to like just assess what's happening, assess if there's any lone pairs to like go about this route, or we can simply take a look at our general formulas over here, right? So what would you guys, in terms of its shape, what shape would our BCl3 be? Cool, thanks, Zinia. It would be trigonal planar, right? Okay, cool, thank you. Yeah, that's where you gave the full answer, right? But we're gonna have to, let's just go through it step by step, right? So we have trigonal planar as BCl3. We know that because we can see that this is where our general formula is matching with BCl3, right? Also, if we were to draw it out, we know boron would be our central atom in this case. But okay, no, it's fine. Let's just stick with this. It's just quicker, right? So then we need to think about polarity, right? So one way we can do it is by looking at the electronegativity difference, right? So if we come over here, we have boron and we have chlorine. So boron has an electronegativity of 2.04 and chlorine has 3.16, right? So if we were to just come back here into the space, 2.04 and 3.16, just had to double check that. 3.16 minus 2.04, which will give us a value of 1.12, right? So again, if we come back to this idea of the scale over here, we need to look at where on the scale does it actually fall, right? And it's falling between this 1 and 2. So then actually, in terms of the bond between our boron and our chlorine, that would be a polar bond, right? But just because there's a polar intramolecular bond, that doesn't mean that the entire molecule will be polar, right? Okay, thank you, Fiabetswe. So you also got 1.12. So what I was saying, let me just emphasize that again. Just because between boron and chlorine, this is a polar bond, doesn't mean that the entire BCl3 is going to be polar, right? Because if we think of the shape, right, which is a trigonal pyramid, right? Oh, sorry, trigonal planar. Sorry, I think the wrong one. My bad. Trigonal planar, right? If we come and look over here, it's a relatively symmetrical looking thing, right? And if you think back if something is symmetrical, it means that there's even distribution of charge throughout the whole thing. Because the reason why our bent and angular things are polar is because those unpaired electrons, those lone pairs, are actually forcing it to bend, right? So if we take H2O again, like this, those lone pairs are forcing it to bend like that, right? And then this gives that polarity, right? Whereas now with the BCl3, because it's trigonal planar, all of them are evenly distributed. It's quite a symmetrical shape. So that's something that the shape actually helps you. If something is symmetrical, then typically it's going to be a non-polar molecule because there isn't that forced change shape the way you do have with a polar molecule like this, right? So if it's symmetrical, it's typically non-polar, whereas an asymmetrical compound or molecule will be polar. Because if it's asymmetrical, these lone pairs and this negatively charged portion is forcing a change in that shape that's making it asymmetrical. Okay, so that's just a little bit of a hint where your shapes can actually help you identify whether something's polar or non-polar, right? So the full answer that you gave in the comments here, here, Betsuwe, where you said it's polar, trigonal, planar, and even distribution of charge. You said it's polar, right? Meaning that there's an uneven distribution of charge. But then you said that there's an even distribution of charge. So in your answer, you kind of contradicted yourself a little bit. And as much as we found over here that the bond between the boron and the chlorine is polar, because the entire thing is trigonal planar, which is a symmetrical shape, the overall molecule would be non-polar. Okay, so this step over here, the one I wrote out, I just did it to show you guys and like bring attention to the idea that just because this bond is polar doesn't make that the entire thing is polar, right? This wasn't necessary because we were looking at the entire molecule, not necessarily the specific bond. Okay, so you were right in saying that there's an even distribution of charge, but if there's even distribution, that means it's a non-polar molecule. Okay, if you need me to re-explain, I'm happy to do that. Just put it in the chat, but I am going to be moving on. Hopefully, just the idea that if you have a symmetrical shape, that means there's even distribution. Even distribution means that it's a non-polar molecule. Okay, cool. Thank you. Okay, so that's all I have for chemical bond. Okay, so you asked me to re-explain. I'm just going to try and phrase it differently, right? So I'll come back to this idea here where we're working with our shape, right? So think of a triangle, right? A triangle is a fairly symmetrical shape in the sense that this side is the same as this side, right? If we had a distribution of charge here, that means it's quite relatively evenly distributed, right? Compared to a shape like a kite. Ooh. Right? A kite, okay, I know it is symmetrical in some sense, but let's say we were going this direction, right? This side's a lot smaller compared to this side, okay? So this is asymmetrical, showing that there's like an uneven distribution of area, let's say, right? So the way that our shapes help us understand whether something is polar or non-polar is if you have a symmetrical shape, let's actually take a circle. That's makes more sense, right? No matter which direction you look at it or which direction you bisect it, right? There will always be even distribution of area throughout the entire circle, right? Because a circle is a symmetrical shape. So because there's even distribution of our area, that means there isn't that polarity, right? So something that's symmetrical means that it's non-polar, okay? Whereas, okay, let me not use a kite. Let's just say this random blob shape like this, right? If we were to go down here, this isn't symmetrical. There's a completely different shape on this side compared to this side. And let's say the area inside here represents the charges, right? So you can see that there's uneven distribution of charge, where this side is more heavily charged compared to here, and this is more heavily charged compared to here, right? So this uneven distribution of charge because of this random shape means that it's polar, because we have oppositely charged ends of a thing, right? So your shape of your molecule helps you understand whether the molecule is polar or non-polar. Okay, so in terms of our BCl3, we looked at our general formula over here. We saw that, okay, it's a trigonal planar, right? Trigonal planar, if you can see here, is a relatively symmetrical shape. It's a triangle. It's like a flat triangle, right? So it's relatively symmetrical. And because it's symmetrical, that means even distribution of charge, meaning that it's a non-polar molecule. Okay, this whole idea of where I actually calculated the electronegativity, this was me just showing you that a polar, you can have, so this is our molecule, right? This electronegativity calculation that I did was specific to this bond, specific to the bond between boron and chlorine. So we know that the entire molecule is non-polar, right? But even a non-polar molecule can have polar bonds, right? Because here we calculated that it was 1.12. Remember here, it falls within this range over here. So it's actually a polar covalent bond. But just because this specific bond is polar doesn't mean the entire molecule is polar. Okay. Unfortunately, if you still don't understand, you can ask me and hopefully we'll have time at the end to go through it again. But I will have to move on just to make sure we get through everything. Okay, so that was chemical bonds and chemical reactions. There is some more theory that you guys need to know in terms of like bond length and that different graph and stuff, but I'm hoping that was simple enough for you guys to understand and not have to work through with me. Okay, so now I'm going to be moving on to intermolecular forces. Okay, so here I want to know what the difference of intramolecular forces versus our intermolecular forces are. So remember at the very beginning, I did tell you guys that the bonds between within the molecule, because this tra section here, that means it's within the molecule, so it's between atoms, whereas our intermolecular forces are between molecules, right? So we've already gone through our intra, so I'll write it here. Intra, we have our ionic, we have our covalent, and we have our metallic, right? So now, what are the intermolecular forces that you guys learn? Someone please list them. List all of them or even one that you know for me in the chat. Awesome. Okay, so we have dipole-induced dipole. You have dipole-dipole. And then we have London forces, which are our dispersion forces, but would not our London forces. Our London forces are dipole-induced dipole and hydrogen bonds. Okay, nice. Thank you to everyone that contributed there. Okay, so for our intermolecular bonds, remember this is between our molecules, right? We do have our ion dipoles. We also have our ion-induced dipoles. Ion dipole and ion-induced dipole, right? So there are quite a lot of them. these three are the main ones, if you will. They're the most tested ones. And they kind of build the foundation of our intermolecular forces, right? So just to explain a little bit more in terms of what they are. So the idea of a dipole means a polar molecule. Okay, so like we said, polar means that uneven distribution of charge. So if this is like my electron cloud that I've drawn around a molecule, this side, because there's high density of electrons here, it's more negative, whereas this side, it's more positive because there's less density of our electrons, right? So this would be considered a dipole because it's a molecule that is polar. It has an uneven distribution of charge, right? So now, between our different molecules that are all dipoles, what happens is they all will look the same because they will have the same ratios and stuff that they bonded with and whatever, right? So they will all have this very negatively charged side and this positively charged side, right? So now what happens is there's actually a force of attraction between here. So this is positively charged, this is negatively charged. Think back to electrostatics. When you have unlike charges, there's a force of attraction, right? So there's actually a force of attraction here between this positively charged end and this negatively charged end, right? And because there's a force of attraction, what happens is that there's a force, there's this intermolecular forces keeping these molecules relatively close to each other, right? And that is what is responsible for our different phases. So whether something's a gas, whether something's a liquid, or whether it's a solid, right? It all depends on our intermolecular forces, right? So this is dipole-dipole that I've drawn out here, where you have two dipole molecules next to each other and the negatively charged end is attracted to the positively charged end, right? Then we have our dipole-induced dipole. So very similar, right? But what happens is you'll actually have this non-polar molecule, right? So you'll typically have all of these non-polar molecules next to each other, right? Or sometimes you would have a dipole present, right? So what happens, let me draw here. What happens is because this is positively charged, as much as this is evenly distributed here, the charges are evenly distributed, we're going to have a force of repulsion between here, right? Because any positive charges that are close to this side will want to get away from this positive charge, right? So what happens is all of those positive charges move there, which result in a temporary and momentary negative edge here, because all the negatives will now be attracted here, right? So this is the idea of induced. Induced means that something else is forcing it to happen or making it happen, right? So these are non-polar, but then because of this dipole that happens to be here, there's a slight shift in the charges here, which naturally will cause this to become slightly polar, right? So not insanely polar like here, where we have this very distinctive difference of charges. But here it's like still almost neutral, almost non-polar, but it's momentarily made polar, and then actually a force of attraction happens here now, because this is negative and this is positive. And then you have this force of attraction between the two, right? So that's what our dipole-induced dipole is. Because there's not a big discrepancy between the difference of charges, this tends to be quite a weak force, right? So this one is quite weak. Our dipoles are quite strong. They're quite sturdy. And then what we have is our hydrogen bonds, right? So hydrogen bonds are specifically when we're binding hydrogen to small atoms like oxygen, nitrogen, and other things, right? If you know the rest, drop them down in the comments. I want to see how well you know where a hydrogen bond happens, right? So those are just two examples. There are more. So put them in the comments what else hydrogen can bond with to form hydrogen bonds, right? So the reason hydrogen bonds are the way they are is it's actually quite a strong force, right? And just because the molecular makeup of the things that it's binding with, it forms this very strong force of attraction, right? Because they are small molecules or small atoms, there's that thing of the atomic distance, right? The distance between your, sorry, atomic radius. So the distance between your electrons and your protons, right? Because they're small, that's quite short. So then the shorter the distance, the stronger the force of attraction between things, right? So whenever your hydrogen's bonding with very small atoms, it will actually form a very strong bond between them, okay? Okay, so we also have fluorine that can be bonded, right? So I'm not entirely sure what BF3 is, but okay, we'll move on. So there we go. So your hydrogen bonds are specific, hydrogen bonded to specific atoms, and these atoms are typically small in their atomic makeup, right? Which results in quite strong forces, okay? Then ion dipole and ion induced dipole, relatively the same as dipole-dipole. It's just instead of having two dipoles, you actually have one ion and one dipole. And remember, a dipole has both charges, so it has both positive and negative, whereas an ion, like let's take a hydrogen ion, will just be positively charged. So naturally, this ion will be attracted to this negative section over there, and there will be a bond formed there. And then the same thing would happen for the ion and induced dipole, right? So there's just a brief explanation of the intermolecular forces that we work with, right? So now I mentioned the idea that the forces help us know what phase stage we're in, right? So if you think of a solid, right, we know our solid atoms in terms of the molecular structure of a solid. All the atoms are close to each other, they're touching each other. There's very little space for them to move. They're very solid and structured, right? So if something is solid, what's happening is, let's say this is my molecule and this is my other molecule. What happens is the force of attraction is quite strong and quite solid, and they're very close to one another, right? So the closer objects are to each other, the stronger the force, right? So this is our solid. If you have a liquid, liquid's almost the same. It's the idea that like they're kind of touching, they're rolling over each other. There's a little bit more space between them, meaning that the force of attraction between the molecules is a little bit less. Some of them are broken, some of them are still there, but it's not so tightly bound as it is in a solid, right? So this is our liquid. And then we have our gas where there's like, they're all just on their own buzz, right? They're all just floating around doing their own thing, not really affiliated to each other whatsoever, right? So the idea of our intermolecular forces is they kind of depict what state of matter we're in, right? Because if we have a lot of forces present, it's most likely going to be solid. Also, the stronger a force is, the more likely it's going to be solid, like at room temperature, for example. Whereas when we start breaking these bonds, we start to have these molecules not be so tightly bound to each other like we have here. They could still be bound to each other, but like this force is being stretched and it's about to break, it's about to fall apart, or some of them are completely unbound, right? So the idea of our intermolecular forces, it helps us depict which phase stage we are in, right? Then you kind of talk about your melting points and boiling points. So the temperature at which we break bonds helps us figure out how strong a bond is, right? So like I said previously, our dipole induced dipole, so our London dispersion forces, right? Our London forces, they're very weak. Equal weak. Dipole, I'm just going to say dipole forces. They're strong. and our hydrogen bonds are also strong, right? So when you think of a bond, right, in order to break a bond, we actually need to provide it energy, right? So to break a bond, we need to supply it with so much energy to the point where that energy ends up destroying that bond, right? So now, obviously, the stronger a bond is, right, the more, okay, the more energy we're going to have to provide to actually break that bond, right? Whereas if we have a very weak bond, we're going to have to supply it with very little energy to break that bond, right? So the idea of boiling points and melting points, this tells us how much energy we're actually supplying to the substance. And then if it has a low boiling point, it's most likely that it has weak London forces because it took very little energy to actually force these bonds to break for it to move through these phase stages. Whereas very strong forces will require a lot more energy, meaning we have higher melting points and boiling points because they required more energy to break the bonds. Okay, so that's where they kind of test you. They'll give you like a list of things and give you different melting points and whatever. And then they'll ask you like, okay, why do you think this molecule or whatever has such a high boiling point? And then you need to draw on your knowledge of knowing which type, firstly, what type of molecule is it? Is it a polar? Is it non-polar? That's where your whole chemical bonding comes into play. And then from there, you need to think, okay, if it is polar, then what type of forces are happening? And then if it's this force, then it's most likely strong, and therefore it has a relatively high melting point because it requires a lot of energy to break that bond, right? So you have to draw on a lot of knowledge for questions like that, but it comes naturally. The more you do it, the more you'll get it and the easier it will get, right? So now here I have just some very brief questions just to work through this. So there's nothing more, there's not a lot more theory without intermolecular forces. You just need to know the different types, knowing how to identify them, and also how the strength of your force relates to melting points and boiling points, right? So here I have an MCQ. The diagram below is used to demonstrate the differences between interatomic bonds, so like your intramolecular bonds, chemical bonds, and intermolecular forces, right? So they ask us which one of the following statements is correct. Okay, X. So firstly, I want you guys to tell me what is X and what is Y. Which one is intermolecular and which one is intramolecular? So which one is a chemical bond and which one is an intermolecular force? Nice. Okay. Let me just see. Okay. Are you sure? So look at where X is, right? So if this is our molecule and this is our molecule, or this is our compound, right? X is the thing between our two compounds. So you, sorry, let me get the name. Tabang, you said that this one is intramolecular, but remember I said intra means inside. So inside the compound or inside the molecule. Here you can see X is actually sitting between the compounds and the molecules, right? So X would be our inter. Okay? Because it's sitting between the molecules and it will depend on, it will tell us how close, well, it will tell us the forces between them. Whereas Y is within the compound, right? And then it's the chemical bond bonding our atoms. Okay, so if you do get confused, it's natural, it's normal, everyone does, especially when you first start this. Intra, or your chemical bonds, chem bonds, are typically between atoms. So if you see Y here, you can see it's between hydrogen and carbon, right? Whereas your inter are between compounds. So here you could see like, okay, it's between these hydrogens, right? But if you were to deep it, this entire thing is a compound and this entire thing is a compound. And now this is a force between the compounds, meaning that it's inter. Okay, so it's normal for you guys to get confused. It is a lot to understand and it sometimes is confusing, but something that helps students is intra means that it's between atoms. So between like a carbon and a hydrogen like we have here, whereas inter is between two separate compounds. Okay. Let me change the color here. So this is intra. Okay, cool. So now let's take a look at the actual questions. They want us to know which one is correct. Okay, so I didn't actually go into relative strengths and stuff. So this one, I'm hoping you guys know just from what you've learned in class because I haven't covered it. But who has an answer for this question? What would you guys answer for this multiple choice question? Okay, cool. Can't see your full name. I'm just seeing Metse. I'm not sure. Sorry if I'm mispronouncing that. But okay, you said C. Let's wait to see what other people say. Who else has an answer? What would you answer this in a test? Treat this like a test where you have to give me an answer. No one else going to contribute? Okay, let's go with C. So C is correct because we discussed here that X is our intermolecular force. Let's discuss A for a little bit. Which one takes a lot more energy? Like, is it easier to melt? Let's take ice, water, for example. Is it easier to melt ice or is it easier to break the hydrogen and the oxygen? Right? Because if you think of how easy it is to break those bonds, that depends on how strong it is, right? So we didn't discuss it now, but typically always your intramolecular bonds will always be stronger than the inter, right? Because this is quite like, I can just hold ice in my hand and it will start melting because I'm warming it up, right? Whereas it's virtually impossible, well, not impossible, nothing's impossible, but it's going to be quite hard for me to actually break the oxygen from the hydrogen. So your bonds between your atoms are a lot stronger than the bonds between compounds. Okay. Then, okay, cool. So C over there. So now here we have a table showing us the relationship between melting points of 3 different molecules, right? So we have methane over here, CH4, which has a melting point of quite a low melting point, right? Negative 182, that's insanely low, right? And then CF4, also quite insanely low, negative 150, whereas the CCl4 only has negative 23. Still quite low, still very cold, but a lot less cold than this, right? Meaning if it's less cold, it means there's more heat. More heat means more energy, right? So just looking at this already, without even taking a look at the questions, I already know that, okay, my CCl4 over here would most it requires a lot more energy because it needs something warmer. It needs to be warmer in order to melt it, right? So it needs more energy compared to my methane, right? Which needs very little energy to actually melt it, right? So remember, we said we need to relate our energy to the strength of the force, right? If something is strong, we need, so again, let's take this very thick, imagine this as a bond, right? If something's strong and it's thick, it's going to require a lot of energy to break that bond, right? Whereas if we have this very thin little bond, it's going to require very little energy, right? So in this case, because this requires more energy, my CCl4 would be a bigger, stronger, thicker bond, whereas my CH4, my methane, will be quite a thin, little scrawny bond. Okay. So that's just me dissecting and understanding what's actually happening in my my table before actually looking at the question. You always need to do that. You really need to sit with something and dissect and understand what's happening with the information that they've given you before you even take a look at the question. Okay, a lot of students tend to just skip over what they've given you here and go straight to the question, which I mean you can do, but it just puts you at a disadvantage because you need to give yourself that context. You need to give yourself that moment to actually understand what you're working with. Okay, so let's take a look at the questions now. Define the term melting point. Easy definition, someone give it to me quickly. Especially if your exams are coming soon, you should know your definitions quite well. They should be at the back of your hand. I said it in the physics lesson, saying it again, easy marks. Absolutely easy marks. You have no reason to miss out on marks for your definitions because they are just giving you marks for free, guys. So make sure you know them well. Especially because it saves you time. If you know your definitions well, you do them right out the bat. You don't even waste time on it, right? So someone, please give me the definition of melting point. Okay, thank you. The temperature at which a compound changes state from a solid to a liquid. Okay, you did add or liquid to a solid. That is the opposite, right? From a liquid to a solid, that would be freezing point. Okay, so they're not interchangeable. For definitions for melting points and stuff, this one would only be from a solid to a liquid, whereas the freezing point definition would be from a liquid to a solid. Okay. Thank you. So there we go. For those of you that didn't hear, I'll repeat it again. Your melting point is the temperature at which a solid is changed to a liquid. Okay, so essentially when your solid starts melting. Okay. Then we have 3.2, right? So let's move on. So they asked us to explain the trend in melting points of the molecules in the above table by referring to the intermolecular forces and the energy involved. So already we kind of touched on that, where we're saying that the trend is that the energy required is increasing, right? Because the melting point temperature is increasing, meaning that we're going to require more energy, right? But now they ask us to make specific reference to our intermolecular forces. So what we first actually have to do is take a look at our molecules and figure out what forces are there between these different molecules. So they all have the same force. Okay, you kind of now need to think of the structure of each of them, right? So I'll draw one out for you. Carbon or methane looks something like this, right? So now you need to figure out like, okay, what is the shape of this? Would this be polar? Would this be non-polar? How does this affect the intermolecular forces that are happening between each of our methane molecules, right? So someone tell me, would this be a polar or a non-polar molecule? No one? No one's sure of what polarity this would be. Okay, so it would be relatively non-polar. Not relatively, it's non-polar, right? Because there's going to be even distribution of our charges. There's no obvious lone pairs, right? So we won't have any more negative region of this. All of the charges are going to be relatively like regulated throughout the entire thing, right? So this would be a non-polar molecule. Because it's non-polar, we need to think, okay, what are the intermolecular forces? So if we come back up here, remember here we have dipole-dipole, which is when we have two polar molecules next to each other. Hydrogen, we're not really working with hydrogen in a small atom, right? So all we really have left is London. And remember I said, with our London dispersion forces, so our dipole-induced dipole forces, we have this non-polar molecules that are present that have that temporary polarity, right? So all of these, they have the same, because they all will have relatively the same structure in the sense that they all have carbon as their central atom. And then we have fluorine, 4 fluorines. We have 4 chlorines, right? So all of them, as much as they'll have different values of electrons, like number of electrons with them, they will all still have regular distribution of that charge throughout all of the molecules, right? And because that's regular distribution of charge, that means we have a non-polar molecule. If it's a non-polar molecule, that means in terms of the intermolecular forces, so the forces between the molecules, we will have London forces, right? And it makes sense because if you think about it, London forces we said are weak. And here this requires so little energy to break this bond. So if it requires less energy, that means it's weak, right? So here it's kind of checking out like, okay, it's such a low boiling point. We need very little energy, meaning that the thing is weak, and we know London forces are weak. Okay, so that's how you need to break up these types of questions. You do have to go all the way back into like chemical bonding and really knowing whether it's non-polar or polar, which sometimes some students struggle with, and some people think it's a schlep, but it's necessary. It's the only way you'll figure out the forces between different molecules. Okay, so coming back to this question, they asked us to explain the trend in melting points, right? And then also referring to the intermolecular forces and the energy involved. So something I didn't reference to, but something you do learn, is that the bigger the molecule, the greater the force, right? Because if you think about it, a bigger molecule has more surface area for interaction, right? So the hydrogen molecule, methane, will be a relatively small molecule, right? Because there's not a lot of electrons happening. The only electrons are here in the center, right? Whereas our chlorine, if you think back to the very beginning when we were doing the shapes, remember how many electrons were around the chlorine, right? So now this is for each and every one of them, right? So this is going to be, in terms of its cloud density, its electron cloud density, it's going to be insanely dense, right? Because there are so many electrons compared to this hydrogen. So, sorry, compared to this methane, right? So in terms of the size of the molecule, hydrogen, we also know, if we think back to our periodic table, it's a very small atom, because this is one of the smallest atoms, it's the smallest atom we have. Whereas chlorine, in comparison, yeah, granted, it's not the biggest, but it's a lot bigger than our hydrogen, right? So when you have a bigger molecule, that means you'll tend to have a greater force, right? Because if you think of like a small molecule like this, there's very little surface interaction, surface area for interaction. And even if it does become a little bit dipole like that, it's still, this isn't very dense, right? So the force of attraction between another induced dipole will be very little, because it's not quite big and there's not that big discrepancy of charge, right? Whereas a bigger one, right, firstly has a lot more surface area to actually interact with. And then also there's just more opportunity for it to have greater polarity. Granted, it doesn't really happen because, again, it's a non-polar molecule and we still have London forces. But because it's a bigger molecule, we'll tend to have a bigger force, right? So increase of our size of our molecule equals increased force. Okay, and you can see that in the general trend over here, because our methane is very small, whereas our carbon chlorine, CCl4, is in relation quite a big molecule, right? So in terms of our answer for this one, let's see, did I leave space? Nice. Okay, so for 3.2, I think it was, in terms of answering this, I'd first specify that all of our molecules have London forces, right? Because they specifically asked us to talk about the intermolecular forces. So all of them have London forces. Then we can say that we can see the general trend is that we're going from a low melting point to a higher melting point, right? And we know that we're going from a relatively small molecule to a bigger molecule, right? So I would say that the size of our molecules increase as we move from the methane, so CH4, to the CCl4, right? And because then we have to relate this. So we say the strength, I'm writing shorthand. Obviously, you guys need to write full words. You can't draw an arrow. But the strength of forces, right, will increase as the size of molecules also increase. Okay. One thing to note with chemistry, what I find is a lot of students write long paragraphs. Okay. I just want to tell you guys that you are allowed to answer in bullet points. Okay. This also refers to physics as well. It makes it a lot easier for you to make sure you're hitting all of your marks. And it also makes it a lot easier for the marker to mark, because your thoughts are more concise. It's not an English paper. You don't need to write a long, lengthy paragraph answer. You can always answer in chemistry and physics. Whenever you have to explain something, do it in bullet point form, because it's the most effective way and efficient way to answer. Okay. Here's just a little tidbit of information. Okay, cool. So then 3.3, they ask us which molecule in the table will have the highest vapor pressure at any given temperature, right? So we need to think about vapor pressure. Vapor pressure means gas, right? So as much as we're working with melting points in this specific example, if something has a low melting point, naturally it will also have quite a low boiling point, right? And boiling point is when we're taking something from a liquid to a gas. So if something starts boiling sooner, right? The longer it has to boil, the increased vapor pressure it will have, right? Because vapor pressure literally means the water becoming gas, right? So if I were to take let's say I have a container, a closed container, and I'm boiling water. The more water that boils, the less water we have and the more water vapor we have, right? The more water vapor we have present, the higher pressure it will be, because we're still in this contained space, but now there's more molecules distributed within the set volume, right? So the more particles we have within the set space, the higher the pressure, right? So when they refer to the highest vapor pressure, they're essentially saying which of these is going to boil sooner and therefore increase the vapor pressure, increase the amount of particles within a set volume, right? This question I could see how some people would struggle to make that connection, especially since we're not really looking at boiling points. But with chemistry, you really need to always think to all the knowledge you have in application of the theory you've learned, right? So because my methane, which is this one, has the lowest melting point, I can assume that it has the lowest boiling point, meaning that compared to all of these, at any given temperature, this is most likely the one to be boiling already, right? Converting to gas. And because of that, my answer would be my CH4 here, right? And my reason would be because it has the lowest melting point. Now, granted, that explanation doesn't really go into depth the way I did, but it's only worth 2 marks. If it was worth 4 or 6, then I'd have to go on a long, lengthy explanation, but I'd get a mark for this and I'd get a mark for that. Okay, so just to re-emphasize, because this has the lowest melting point, it will naturally have the lowest boiling point compared to all of these. Therefore, at any given temperature, it's most likely the one to already be boiling, right? It's already the one that's already being converted into gas. If it's being converted into gas, we're going to be increasing this vapor pressure within this chamber, if you will, in the set scenario, meaning that it will have the highest vapor pressure at any given temperature. Okay. Then 3.4 asks us, or tells us, water, H2O, is a smaller molecule than CCl4, but water has a higher melting point than CCl4. Explain this observation by referring to the type of intermolecular forces. So now I want you guys to tell me, why do you think water has a significantly higher melting point? Because if you think about it, water's melting point is actually 0 degrees, right? And its boiling point is 100 degrees, right? So why, where our CCl4 is at -23, why is our water a much higher temperature, even though water is a much smaller molecule compared to our CCl4? Someone tell me in the chat by referring to intermolecular forces. Awesome, Simba. So you said because water has, you say is a hydrogen bond, but water has hydrogen bonds. Okay, just make sure your phrasing is correct, right? So remember we said hydrogen bonds is between hydrogen and small atoms like oxygen, right? So water, in terms of its intermolecular forces, actually has hydrogen bonds. So in terms of my answer here for 3.4, I would say H2O has hydrogen bonds. Right? It also does have London bonds, London dispersion bonds, but this is the reason why our boiling point and melting points are so high, right? Then we need to talk about, because remember, this is worth 2 marks, okay? So we kind of need to give a bit of an explanation. This wouldn't be enough, right? The reason why water has a higher boiling point or melting point is because hydrogen bonds are stronger, right? So you actually have to specify that. So you'll say hydrogen bonds are stronger, therefore require more energy to break the bonds. And remember, if we require more energy, that translates to our temperature, right? So that means we would have a higher melting point or boiling point because we have to provide it with higher temperatures in order to break it. Okay, so that's how you should have answered 3.4. And then the last question for this section is to write down the name of the intermolecular force that will exist in a mixture of water and CCl4, right? So now you kind of need to think of the individual polarity and think about like, okay, what type of intermolecular forces will be exerted between these two molecules. So you need to think back the way we tracked back here, where we had to figure out if it's non-polar or polar. You're going to have to do the same here, right? And then from there, figure out what type of what type of intermolecular force there is. So can someone tell me the H2O, is it polar or non-polar? We did work with water a lot in the beginning, so you guys should know because I drew it a few times. Think of its lone pairs. How many lone pairs does it have? If it has, does that make it polar or non-polar? Cool. Thank you, Simba. Water is polar, right? So water's polar. We did discuss, and we've already figured out that the CCl4 is non-polar, right? So now if we have a polar molecule and a non-polar, let's go back up here. Think about what intermolecular force we'll have. It will most likely be this here, our dipole-induced dipole. Because we have a non-polar molecule, we have another polar one. So this one can temporarily and momentarily induce polarity in this one, which will then have that force of attraction between them, right? So in terms of the answer for 3.5, the answer would be dipole-induced dipole forces. Okay, so that's it for intermolecular forces. So that I stuck on those two for quite a while, and just going through it quite thoroughly, just because I know this is all you've covered in chemistry so far, because I know the year has been very physics-based for you guys so far. So I did prepare some stoichiometry, just to, because I think that is one of the next sections you're going to be working through. If it's not fresh on your mind, don't stress. I know it's something from last year. We do have some questions here that I thought we could work through, but there isn't much time. We have I think we are still going to 8:30, so that's like a little bit over 10 minutes. So what I'm going to do is, if you guys have any questions, please drop them down in the chat. I'll spend the last 10 minutes kind of working through any concerns you guys have. But while we do that, I think I'll just give you a brief reminder of stoichiometry just in the meantime. Just because, yeah, it is there. You tend to, in grade 11, it's very important, and also in matric, like you find it throughout the whole of chemistry. So it's important to just keep your brain fresh of what it is and remind yourself of what it is. So yeah, if you do have any questions, drop it in the chat. While I wait for any questions to come through, I will be kind of just giving you a brief reminder of your stoichiometry, right? So stoichiometry is all about calculating the amount of substance we have in different chemical reactions, right? So we're always working back to this idea of a mole. So the mole is literally the SI unit for amount of substance. A lot of people don't truly understand what that means. It is quite a foreign concept, right? Where we're working, the mole is kind of just allowing us to work with such small quantities in a quantity we can actually work with. Because if you think of atoms and chemical reactions and stuff, it's also minute. It's literally on an atomic level. So what the mole does is it allows us to take values from such a microscopic scale and scale it up into values that we work with, like grams and liters and concentrations and stuff like that, right? So typically with your stoichiometry calculations, the first step is to always just figure out your moles, right? So we typically work to find our moles, and then we work to calculate the concentrations and mass and a bunch of different things using our moles, right? So we have a bunch of different formulas in stoichiometry that I've written out here. So we can calculate our moles from our mass, right? Where we have, so another way this can be written, let me just write out where we, so if we are trying to calculate our moles from our mass, we obviously just manipulate this a little bit. So moles will be equal to mass over our molar mass, right? So you typically just learn these formulae just to be able to do any conversion between mass and moles and stuff like that. Then there's some very little theory in this topic. It's more about calculations, but I guess you kind of just need to know which values to use when. So specifically for mass, we have this idea of molar mass, right? So here I've written in yellow that your molar mass is the mass of 1 mole of a substance, right? So 1 mole of oxygen will be 16 grams, right? So it's just this idea of converting 1 mole of oxygen to a tangible mass that we know that we can work with, right? So here I've drawn what you see on your periodic table, where you have your atomic number at the top, and then at the bottom would be your atomic mass, and this is the mass that you use when calculating your molar mass, right? Then you have something like concentration. In terms of your definition of your concentration, it's just the amount of substance in a solvent, or the amount of moles per unit volume, right? So if you think of OROS, if you're making OROS quite concentrated, you are putting a lot of OROS in a small volume. Whereas if you're making something more dilute, so less concentrated, you're putting less amount of substance in a bigger volume or in the same volume, right? And then you have this idea of volume, where you typically use a molar volume, right? So molar volume, and this specifically, it's typically this value, typically this constant value, but it does differ based on the different temperatures that you work with. So for your molar volume, you typically have to have STP, which is standard temperature and pressure of 0 degrees and 1 atmospheric pressure, right? But this value can change, and they typically do tell you if it's different based on different temperatures and pressures that it's exposed to. Okay, and then you also have this Avogadro's number, which helps you just calculate the actual number of particles found within 1 mole of a substance, right? So when you're calculating the number of particles, you would multiply your moles by Avogadro's constant, which is the 6.022, right? And this is typically the amount of particles that you have in 1 mole of any substance. So when you're trying to find out the number of particles in X amount of moles, you just have to multiply the two numbers together to find the total number of particles within that substance. Okay, so we don't have enough time I think limiting reactants, I'm realizing that maybe you're only going to learn that this year. So actually, I'm not going to go into this because I don't think it would be revision. It would be new work. And then obviously we don't have enough time to go through the questions that I've put here. But I don't see any questions in the chat from everyone. So I hope you guys enjoyed this explanation. Hopefully it taught you something. Hopefully you feel a little bit more confident in approaching certain questions. Thank you again for joining. I know, sorry again for the delay in the beginning. But good luck for all of your exams. I really do appreciate you guys taking the time to come here, and hopefully you learn something and take a lot away from the session. Thanks, guys.